Good afternoon, everyone. Today we're going to continue our study of time series analysis, in particular working on ARIMA. Okay. Okay. I gave you this file, class. So maybe let's take a look at some of the may question lang dito are the Saturday alternative class done via Zoom. Via Zoom, no? Sorry. Via Zoom. I'll have a Zoom meeting. Magzo-Zoom class ako, no? And then you can join. If you're free, you can join that Zoom class. But again, I'll not call the attendance. Okay? So thank you, Chloe, for the clarification. All right. So let's open this class. Let's open this site. Control C. Let's just use ko lang to. Control V. So this is from Penn State. Oh, I'm not sharing my screen, sorry. Oh, sorry. Share. Okay, thank you. Okay, so the first one that I shared with you contains some information about the ARMA process. Okay, so this one, for example, which we discussed before, is an MA process, MA1 process. So you have your time series, x sub t, is equal to a certain constant plus your error term, that's W or epsilon, others call it epsilon, epsilon sub t plus theta 1, epsilon sub t minus 1. So this is a first order moving average. Okay. For a second order moving average, you have your constant mean plus your error, your residual at time recurrent error, epsilon sub t. And then you have your first order, theta 1, epsilon t minus 1, or here W, and theta 2 times W sub t minus 2. So this is your MA, or in general, MAQ, which is your X time series is equal to, you notice how epsilon sub t or W sub t is written first after the constant, mu times W sub t or epsilon sub t, and then you have your theta 1, theta 2, theta q. Okay, this is the qth order of moving average. Okay, and there are certain conditions here, class. Okay, so the mean is equal to a certain constant mu. The variance is given by this formula, and then the autocorrelation function, which we're going to study in the future. Okay, theta 1, okay, is this equation. All right, so okay, so here are some examples, and here are discussions for ACF and MACF. Then there are some, if you want to learn more, class, there are some R codes here that you can copy and run in your RMD file. Okay, so this is your MA, and in the other discussions, you have also, where's your AR? Okay, andito si ARIMA. Where's AR? Okay, I don't see AR. Anyway, so we're going to have discussions on this, the PACF, the ACF, as in the next few sessions. Okay. All right. So you can see here some concepts about invertibility. We're going to discuss that. Okay. And if you have time, class, you may copy this because this gives us, for example, this will now generate an ARIMA model. It will simulate an ARIMA model. Okay, so if you want to do some advanced study, okay, so this is an example class. Your time series is equal to a certain constant 10 plus your residual plus this is your theta 1.7. And you'll notice that your thetas, okay, theta 1, theta 2, they follow a certain rule. Okay, and we'll discuss that. Okay, let's go back to our code. Okay, I will not show anymore here the other lessons. Okay, except for this one. This is an excellent source. Okay, let's take a look at this. Duke. This is from Duke University, Control C. Yeah, these are very good references for you to use. Some of you are requesting for some materials. I'm giving you some here. Okay, so this is, okay. This is your ARIMA here. Introduction to ARIMA. Okay, so let's see. These are PDF files. Okay, there are some PDF files there. Okay, so you may download this. Okay, ARIMA models, autoregressive integrated moving average. Okay, are an adaptation of discrete time filtering methods developed in the 1930s to 40s. The original discrete time filtering. So it was George Box and Gwilym Jenkins who developed this ARIMA in the 1970s. That's why it's sometimes called Box-Jenkins method. Okay, so what ARIMA stands for, I just wanted you to see, class. Okay, ito yung PDQ natin. Okay, number of autoregressive terms is P. Number of moving average terms is Q. That's your ARIMA PDQ. All right, so I leave you, class, to just peruse over this and take a look at what these references can provide for you in your search for knowing something more about the ARIMA model. Okay, so I hope you have run these packages. So we'll have forecast, FPP3, quant mode, time series. Some of these were running for the first time. I think FPP3, URCA, TSM, perhaps. So once you have run this, of course, if you see that, for example, you're running this code chunk and then it tells you that there's no package called FPP3, what do you do, class? You install first FPP3. Okay, because this assumes that these packages are already installed in your computer. If not, then you'll have to install the other, that particular package. The others will load already, but those that are not yet currently installed in your computers will have to be installed. And you know how to install it. You can use the code command install that packages, or you can just go here to packages and then install, or go here to tools and then install packages. So many ways to install packages. Okay, I'll give you a few seconds, please, to please chat in the chat box if you're done loading these packages. I'll pause recording first. Please remind me to. Okay, so now that you have loaded the packages, I have here some text. So we learned before that time series analysis is very important. Time series data has its unique characteristics. And we said that in order to model a time series, there are several ways that you can do this. And one of the most powerful ones is the ARIMA model, autoregressive integrated moving average. The ARIMA method was developed by George Box and Gwylin Jenkins. That's why it's called a Box-Jenkins approach. Okay, and we learned last time that ARIMA stands for AR, where we use the past values of the time series itself, MA, past error terms, and AI, integrated, means you have to difference the data first. Okay, because we said that we can only use ARIMA if the data, time series data, is stationary. If the time series data has a trend and a non-constant variance, non-constant mean, then we'll have to transform the data before we can apply ARIMA to it. Okay, so we discussed this last time already. So this is an example of an AR1 process. Okay, could you tell me please if your LaTeX is running? If you press enter, because in my case, it's not running. How about in your case, class?
Sure.
Yes?
Are you sharing screen po? Because on my end, I can't see your
Ah,
screen.
wala. Oh, sorry. Oh, yeah, sorry. I,
Mm.
all right. Thank you. Thank you for reminding me. I stopped sharing when I asked some of your classmates to share their screen. Thank you. All right. So we have this Box Jenkins approach. And then can you tell me, class, if this LaTeX enter, is it running on your end? Does it print this equation, this equation? Kindly chat, please, if it's running. Okay, good. Thank you. How about the others, class? Okay, good. All right, good, good. Unfortunately, class, I'm having a problem now with my R. Okay, it's not running on my end, but what's important is that it's running uh, uh, on your end. All right, so we have this alpha 0. This is a constant plus phi 1. Okay, as we said, this is like regression. This is the coefficient of your first order, first lag, first order AR process, and then your residual epsilon sub t. Okay, we said last time that this is like a regression model, and this one is your actual value, observed value. Okay, this is your predicted value. This is the model value. And we said that the difference between the actual or observed value and the model value, okay, in order for this to be equal, we have to add this residual or error term. Okay, this epsilon sub t. Okay, so now what's important to note is that your epsilon sub t, your epsilon sub t, okay, this one class, your epsilon sub t, this one, epsilon sub t should be white noise. So we described white noise last time. We said that white noise does not have any trend and it does not have any, uh, its mean is constant and its variance is constant. Okay, constant mean and constant variance. So this is our model. Okay, and in order to for this model to be valid, your epsilon sub t should be white noise. That's why after you create your model, you don't stop there. You don't say that, oops, the model is finished, the model is created, we're done. No, you will have to, we will have to assess. We will have to do what we call diagnostics and check if your epsilon sub t, your residuals, is white noise. If it's not white noise, if it has a trend, or if the variance is not constant, then our model is unsatisfactory. Okay, so that's one thing, one very important thing when we do ARIMA. The final step before we even forecast is make sure that your that your residuals are white noise. In the event they're not, then perhaps another method might be the better approach to your time series. Okay, so continuing class. Okay, we also discussed random noise. What's random noise? Okay, random noise, we said, is a type of time series that has trend. Okay, the mean is not constant, and the variance also is not constant. Okay, and the equation for a random walk is this one, class. Here, your y sub t is equal to your past value at lag 1 plus your epsilon sub t. Notice how different this is from your ARIMA process. Your ARIMA process has a phi here, phi 1. And that phi 1, the condition of that phi 1 is that it has to be less than 1. Okay? But in this case, for your random walk, your phi, okay, is equal to 1. Okay, so that's a very important distinction. Okay, take a look again at your random walk. Y sub t is equal to y sub t minus 1 plus epsilon sub t. So there is actually a phi 1 here. However, your phi 1 is equal to 1. Okay, so when your phi 1 is equal to 1, then you have a random walk. Okay, an ARIMA process, an AR process should have a phi here, which is the coefficient of your y sub t to be less than 1. Okay, so please take note of that distinction. Okay, so once again, an AR process class for modeling AR1, for example, we have this equation, and the condition is that your epsilon, your residual, should be white noise. If it's white noise, then if it's not white noise, then something's wrong with your model, or that should not yet be the final model. Okay, so to generalize class, so AR2 is just, you have you have first order of your past values, and then you have a second order of your past values. A2 here is your phi sub 2. Okay, so phi sub 1 and phi sub 2. So you have two orders. That's why it's called AR2 process. And in general, your ARP process is here. Okay, I don't think I gave this to you, so in the other section, I let them write it. Okay, so I'll give you a few seconds, class. Please write this one, ARP process. I suggest you copy the AR1 and then just copy paste the phi and the y sub t. Once you're done writing your ARP process, class, please chat in the chat box that you're okay. Thank you. Let's wait for the others to finish and then check your printout. I'm sorry again, I'm not able to print my LaTeX. Good. Thank you. So you can see that for an ARP process, okay, as we discussed a while ago, where's that example that we had? Was it this one? Okay, where's that one? Okay, wait. Just for us to be precise in our language. Okay, you can see your class. Okay, so we have here fifth order of autoregressive. Okay, for your ARP, fifth order autoregressive model. Okay, now we go to the next one, which is your MA. Your MA class, as we, if you write this class, you have your, uh, you can write your constant here. So maybe I'll go here. Here, actually, we discussed this a while ago, right? So this is your MA1 process. Only the representation of the variables is different. So this is your alpha null. Okay, this is your average. Okay, plus this is your epsilon sub t plus theta 1 epsilon t minus 1. So if we go back here, class, this is your alpha. This is your constant in that website that we used, uh, that we looked at. It used mu. Okay, but they're the same. It's just a matter of representation. And then we have your epsilon sub t, which is your W sub t in the site that we looked at. And this is your theta 1, okay? And then epsilon t minus 1. Okay, so you can see the difference between your AR process. The AR process uses the autoregressive, okay, lagged values, okay, self values of itself, while your MA is your past residuals, error terms. So you know how to write this class. Your time series y sub t is equal to a certain constant plus your residual plus theta 1, theta 2, theta 3 up to theta t minus q. Okay, this is your qth order moving average. This is your first order moving average, second order moving average, etc. Okay, so let me pause for a while, and I don't know if I shared this with you, but if you're copying it, if you're doing it, I'll give you a few seconds to work on that for your MA order queue. When you're done, kindly chat, please. Okay, so we have discussed, class, an AR process and an MA process. Therefore, the combination class is just very easy. You just combine both the AR component and the MA component. So in this example, you have an ARMA 11, you can see here that this is the time series is equal to your intercept or your constant plus this is your first order autoregressive. And then for your MA1, we start with your current residual plus your uh, first order first order MA, I'm sorry. So this one has a double, okay, just kindly correct it. Okay, for this one, you actually don't need this. P1. All right. So ARMA 11, you have your uh, first order of AR and first order of MA. Okay, so the equation will be like this. Okay, so in general class, ARIMA PDQ, okay, ARMA, let me erase this, ARMA PQ, okay, or ARIMA PDQ. The insertion of D class means that the data that you're looking at is different. If you recall, the air passengers data set that we were using, if you're going to use, if you're going to model that AP or air passengers data set, then D will have to be 1, which means that you'll have to difference the data in order to make it stationary. Okay, so we'll have more examples of this as we go along. Okay, so what are the general steps when you're using ARIMA? Number one, you should make sure that your data is stationary. If your data is not stationary, then you will have to transform the data. How do you transform? Okay, you transform by you first have to deal with the non-constant variance. Okay, so technically this should it's best that this comes first. Okay, because we learned last time that we do have to uh, log transform first before we get the difference. We cannot get the difference and then get the log transformation. What's the purpose of getting the difference? The purpose of getting the difference is to detrend the data. If the data has trend, if the data has non-constant mean, then the remedy for that is to get the difference of the data. Okay? If the data has non-constant variance, then to remedy that, you can get the log of the data. If it has both non-constant mean and non-constant variance, the initial step is to get the log transform and then get the difference. Doing otherwise will mean that you'll have NA values, and that cannot be. Okay, because you cannot get, when you get the difference, there could be strong possibility that there will be negative values. And when you get the log of a negative value, that's undefined. So that's an NA. All right. So technically, this should come first. So why don't we do that? Control X, okay. Control V. So maybe you can put here if if data is has non-constant variance and non-constant mean. Okay. So in this situation, we do log transformation first, step 2, okay, and then get the difference of the data. Okay. Okay, so after you do that, then you check again, of course. Why? Because sometimes you might need to difference twice. Okay, usually in log transformation just once. I haven't seen a data set where I have to do two log transformations. So log transformation is one, and then difference, sometimes we might need to do double differencing. Difference first and then difference again. Okay? All right. Then check, of course, visually if the data is already stationary. And you can also do statistical tests. You have the ADF test. ADF stands for Augmented Dickey-Fuller Test. I'll show you an example later. And then the next one is, okay, we will not discuss this yet, plot the ACF autocorrelation and then partial autocorrelation function. What's the purpose of this? Okay, because once we have stationarized the data, then we will have to determine, is this an AR process, an MA process, or an ARMA process? How do you do that? You have to plot the autocorrelation ACF function and the PACF function. Now, mind you, this is not easy. Okay, if you're going to do this manually, okay, I'll explain how this is done manually, and it's quite very, very laborious. Okay, now, fortunately, may R, no? Kasi isang ano lang yan, isang code lang yan, no? And then it will plot already your autocorrelation function and partial autocorrelation function. The challenge is to make use of these plots that was generated by R to determine an initial model. Kasi class, it's not easy. It's not easy to determine the model using ACF and PACF. So it will be more of a trial and error. Okay, try this, check, try this, check it, try this, check it. One good thing is that with the advent of software like R, madali na yung class. Isang code lang, tapos it already gives you the suggested the suggested model. Okay. All right. Then after you have identified the best or optimal ARIMA model, you'll have to once again plot the ACF and PACF. Okay, what's the purpose? The residuals have to be white noise. If the residuals are not yet white noise, then it means that your model is not satisfactory, or you might use another model with ARIMA. Okay, so this is in particular very true if you have volatility clustering. Okay, I'll show you examples of this. Volatility clustering, so ARIMA model might not be sufficient. Okay, so we might combine it with GARCH. Okay, and after you have the final model, then we forecast. Okay, so this one we have discussed before. We said that stationary time series, the statistical properties are that the mean, the variance, autocorrelation are all constant over time. Okay, it has the property that the mean, variance do not change over time. Okay, stationarity looks like a flat looking series. Okay, so flat looking series, but looks like this, like that. It's flat. Okay, no trend and no seasonality. Okay, non-constant variance. Okay. Now, why? Why is it important, class, for us to make use of a stationary time series? Because it makes modeling a lot easier. A stationary time series is one whose properties do not depend on the time at which the series is observed. What do we mean by that? Remember the plot class or a stationary time series? If you go to this period, the mean will be the same, the variance will be the same. If you go to another period, same. Constant mean, constant variance. Okay. Time series with trends or with seasonality are not stationary, as mentioned. Okay, so let's take a look at this. Okay, maybe the second one. Let's copy this and take a look at the plots. Although we have discussed this, okay, but let's just Control V, and I'll just show you. Okay, this is stationary. Okay, this looks like more a random walk. This is class non-stationary, has decreasing trend, and then here this period increasing. Okay, although the variance might look constant, but definitely it's not stationary in mean. Okay, so if you take a look at this, here you have constant mean, constant variance. Stationary mean, stationary variance. Here you have the mean is not constant, but the variance is constant. So you'll have situations like that, wherein you have stationary in mean, but non-stationary in mean, but stationary in variance, or vice versa. You have the mean stationary, constant over time, but the variance is not, so non-stationary. Okay, so these are the examples of a stationary and non-stationary time series. Okay, so let's move on here. Okay, we discussed last time that white noise class is stationary. It does not matter when you observe it. All right, so as we said here, a stationarized series is relatively easy to predict. Okay, we'll just have to predict its statistical properties. Because we know that it will be the same in the future as they have been in the past. Okay, and as I said, take note that when you model a time series that has been logged, you got the log of it, and then you have differencing also. You're already modeling a different time series. Okay, di ba yung difference log ng AP, ng airline passengers, it's different from AP. Okay, it is a different data. Okay, so what's the use of that when you're now modeling a different data, and when you get the forecast, it will not forecast the original data. Okay, the good thing is after you have created the model, okay, you can untransform your data. You can reverse. If you get the log, then you can get the exponentiation. Okay, if you get the difference, then you can integrate that. That's why it's called integrated. Okay, you can add what you have deducted before. So walang problema. There's no problem in modeling not the original data, because we can revert back to the original data. Okay, that's an important thing to realize, class. Okay, for this one we did this before, class. So just have quickly we can quickly run this. I'll run this, class. Data and air passengers. Okay, so we know that this is a vector of time series. It appears in the values and not in the data. Okay, so we'll create an object called AP, and it's the same content as air passengers. Let's view, and then get the first 24 observations of this, Control Enter. Okay, here. This is our view, and our head is here, first 24 observations from 1949. Okay, I'm going through this fast because we have already done this. Now, let's take a look at other functions. So if you get the structure of airline passengers, what are we getting, class? It tells us some information about the data. It's a time series data. It's a time series vector. Okay, from 1949, actually this is 1960. Okay, 144 observations. So are there missing values? We can use this function. Sum of V is an A of the object. Okay, so there are no missing values. The frequency, we have run this before, 12. This is monthly data. And the cycle, let's take a look at the cycle of AP. There you go. So you have from 1949, January up to January, February up to December. Okay. So all the ones are one. Number one, January on. All the number twos are February up to December number 12. So this is very important. Okay. For the summary class, it will just give us the 6-number summary. Okay. All right. Let me pause for a while, class. And are there any questions so far? Any questions? Are we clear so far? Okay, good. Thank you. How about the others, please? Okay. All right. So let's plot, class. We have plotted this before, actually, just using the plot function. So it's same here, plot function. We're going to plot AP. We just gave it some labels. X label, date. Y label is passengers, and the main plot. And then we print. Let's run this. So there we go. You can see that air passengers is not stationary. As we discussed last time, it has a trend, non-constant mean, and even the variance seems to be non-constant. Okay, not non-constant variance. Okay, so it violates both the rule of stationarity. Therefore, we cannot, as of the moment, we cannot use ARIMA for this. We have to do some log transformation. Okay, this is another way. This is from GG45 using the auto plot function. It will give us the same plot, only it's cleaner. Okay, this is cleaner than the previous one. Okay, so now let's take a look at this. We're going to ask R to create a box plot. If you recall from your basic stat, a box plot consists of a box with whiskers. You have your minimum, maximum, first quartile, second quartile, third quartile, and some outliers, if any. So the function is box plot, and then AP. How will the box plot be created? It should be based on the cycle of AP, which means that all the ones would be January, February, etc. Okay, so let's run this box plot one. Okay, there you have it. There. And notice that since we use cycle here, AP should be associated with the cycle of AP. So a while ago we ran cycle, right? And it's 1 to 12. And 1 pertains to the first month. So this is the box plot for January, February up to December. So this is monthly because of the cyclicality. Okay, and you can see here that the most number of airline passengers is in July and August. The median is the highest is at August, and next in July, and next in August. The 7 here pertains to July. 1 here pertains to January. And the lowest looks like November and February. Okay, so you can learn some things about the nature, the behavior of your data, in this case, airline passengers. And notice also that there are no outliers. We don't have here points. Okay, because if there are outliers, then box plot would have determined that. Okay. All right. So here are just some thoughts about the data. More passengers traveling in month 6 to 9 with higher means and higher variances than the other months. Okay. So indicating a seasonality apparent in the cycle of 12 months. So when you plotted this, you notice that there are upticks there, and that occurs in month 6, 7, 8, 9. All right. So now we can decompose. I'm sorry, I have to move a bit faster, class, because we have to be on the same page as the other section. Now, there's a very powerful uh, function called decompose. So this comes from your stats package. Okay, and you don't have to install this because it comes preloaded. So I'm creating this object called decompose add, which is for additive. So we said that the seasonality could either be additive or multiplicative. We can model it as an additive seasonality. So the function is just decompose AP additive. And when you're modeling it using additive seasonality, this is the equation. Your y sub t is equal to your trend plus the seasonality plus a certain random term. The random term is those that cannot be part of your seasonality or your trend. Okay, so that's the random part. And then let's plot this, auto plot this object, decompose AP additive. If we run this, we can see now the breaking down. It's really decomposing it. So that's why it's called decompose. So this is your original data. Okay. And then you can see here this is the random component. This is the seasonal component, and this is the trend component. And you get your actual value by adding your trend plus seasonal plus your remainder or random. Okay, so this is the formula. Or we can make it multiplicative. So this one. But this time it's y sub t is equal to trend times seasonality times the random component. Okay, the plot does not so much differ. Okay, it's the values that will really differ. Okay, so this is your original. This is your random. It's a remainder actually, and then your seasonal, and then your trend. All right. So uh, we can actually test. Okay? So let's test your your time series, because when we took a look at AP, we said that it's not stationary. That can be verified statistically. So there's this function from the T series package called ADF.test. So we'll use this, and then the object is AP, and then alternative is equal to stationary. So which means that the null hypothesis is the time series is non-stationary. And then K is equal to 12. We can use anything usually. It's 12, 18, 24. This is just the lag. So if you run this class, okay, so what do you see here? Data is AP, augmented Dickey-Fuller statistics, negative 1.5. Log order is equal to 12. P-value is 0.7. Okay, so how do we conclude, class? Is the time series stationary or not? So time series, is it stationary? Now the p-value is 0.78. So it's very much higher than 0.05. Therefore, we will have to reject the null hypothesis. Okay? That the time series is not stationary. Not stationary. So we will fail to reject. We cannot reject this class that the time series is not stationary. Okay? we cannot reject that hypothesis. All right, which actually is what we were expecting kasi the time series is really not stationary. Okay, now, okay, you recall we did this last time. So I want you to run this. Okay, remember our AP object. We get the log first and then get the difference, not the reverse. Okay, when we got the difference log of AP and then plotted it, okay, you can see that it's now stationary. Okay. But if we test it, let's test it using this one. So I suggest you write this class. Okay, I'll give you a few seconds to run this. But this time what we're testing is DLAP. Okay, same function as above, only that we're not testing AP. What we're testing is DLAP. And we know that DLAP is stationary. Okay, constant mean and constant variance. If we run this class, what do you get? All right. So the p-value is 0.06. And this is also still greater than 0.05. Okay, greater than 0.05. Then, conclusion, we also fail to reject the null hypothesis that the time series is not stationary. Okay, although the p-value is quite close to 0.05. So this is one weakness of the ADF test. Okay? Medyo may bias siya towards being non-stationary. Okay, this one ADF test. Now, how about, I want you to look down, class, here. And here, meron dito, no? Ito. May isa pang test. Okay? It's a KPSS test. It's the Kwiatkowski-Phillips-Midshин. Haba ng pangalan. Okay? So the null hypothesis here is that their time series is level or trend stationary. Okay, maybe let's copy this here. Control C. And let's put it above here. Although anyway, we're going to discuss that next meeting. Okay, and I'll close this. Okay. I'll remove this. Okay. Take a look at this class. So we will have to change this by DLAP. Okay, because this is what we difference and we log and difference. Okay, so the KPSS test is a more powerful test than the ADF test. So here, the null hypothesis is that the data is trend stationary. What does that mean? When you say trend stationary, it means that the data has constant constant mean, right? Okay, so does a DLAP have constant mean? Let's see. Okay, so this is the null hypothesis. So the null is equal to trend stationary. Let's run this. Okay, and then what do we have here? The p-value is 0.01. Okay, what's our null hypothesis? We're saying that the null hypothesis is the time series DLAP is trend stationary. So trend stationary means it does not have its average is constant average, right? And what's our p-value? Our p-value is 0.1. Okay, which means that we fail to reject, since this is greater than 0.05, our conclusion is we fail to reject that the null hypothesis, we fail to reject the null hypothesis. So there is strong statistical reason to believe that your time series is not stationary. Is is trend stationary. Okay, so there's a difference between the KPSS test and the ADF test. Okay, so I think yeah, we reached up to this far. So next meeting we're going to discuss ACF, PACF, and all the other stuffs that are very important uh, for ARIMA modeling. Okay, so let me